Welcome back to the discussion of spatial query languages. In last few videos, we talked about the notion of queries, query languages. We looked through the old SQL, and we also noticed how tedious it was to express spatial queries in the old SQL. Okay. So now we are coming to the main topic of this particular chapter, and we are going to go look at OGIS library, which supports spatial data types and operations and is used within SQL. Okay. So at the end of this section, we should all be able to recognize spatial data types and operators which are provided by OGIS library. And this in particular is one library called simple features within OGIS. Okay. All right. And we'll also look at a couple of very simple queries which do not use spatial joins and try to use simple operators like distance or area, which are probably familiar to many of us. Okay. So before we go there, let's first see how SQL changed, which allowed us to add spatial data types. So essentially SQL has gone through many standards. The first one was in 1986, sometimes called SQL 1, and that's the first standard which was very basic. Okay. The second one came in early 90s, fondly known as SQL 2. It added some more features for spatial join and so on. For basic join, it added keywords. But really for spatial data type, the major change came in 2003 and fondly known as SQL 3. Since then, you have had another version in 2008. Okay. But SQL 3 added user-defined data types. So it gave you ability to go beyond the built-in data types of numbers, currency, and so on. And then many different vendors took advantage of that to add spatial data types. Okay. So the OGIS is implemented in most SQL system through this user-defined data type facility of SQL 3. Now, what is inside OGIS? Okay, so OGIS again is a standardization body, and they have proposed many different libraries. The one we are going to look at is called simple features. That was the first standard they proposed, and it is widely adopted. Inside that standard, you see about half a dozen spatial data types. So things like points and polygons you are going to see here. In addition, it also provides many operations. So distance, area, inside, those kinds of things are now supported directly. So you don't have to come up with its logic and look for how to compare polygons with points and things like that. Okay. This standard actually started in mid-90s. It was based on very sound mathematical principles. In fact, there was a thesis by Max Egenhofer, completed in late 80s, which was already used in some GIS packages in ESRI. And it was a basis for the topological operations here. And many vendors very quickly came on board. The ESRI, which is the GIS vendor, the Oracle and IBM, the database vendors, they came on. And since then, public domain databases like Postgres and now even MySQL and so on are using this. Okay. So let's go look at the data types. The main data type of interest to us is this data type called geometry. And it is going to model geometries in 0 dimension, 1 dimension, and 2 dimension largely. And those are the subclasses. So essentially for 0 dimension, it models points. And these points usually have an x coordinate and a y coordinate and a set of operations. Then it also has 1 dimensional geometries such as curves or line strings. Okay, so line string is related to the straight lines we all know. But it essentially is a sequence of straight lines which are connected. So if you were thinking about a river which snakes around, then it's hard to model it as a single straight line, but you could model it as a sequence of straight lines which are connected, and that's a line string. And then finally polygons. So for the 2-dimensional geometries, it provides you polygons. And again, we'll treat these polygons to be very simple now, but in general, these polygons can have holes or other details in there. Okay. So this is very intuitive. If you took any geometry in your junior high or high school, you probably learned these kind of data types and you know these very well. But when you bring this to database query languages like SQL, then you have to worry about one other consideration, and that mathematically is called closure of an algebra. Okay? But let me explain this to you in English. The basic idea is that in SQL, we may start with a collections of points or polygons and so on, and then we perform some operations. The operation may be geometric intersection or geometric union, But oftentimes we may want to store the result back in the database and do a subsequent query. Okay. So, if we want to compose these queries, then it is important for the result to be also represented using the data types we are already providing. Okay. So, that is an objective in SQL kind of query languages. So, essentially these data types have to form an algebra with a closure property. Now, if you only look at points, lines and polygons, that property does not hold. So, just imagine you had a union of 2 points which are not on the same location. Now, what you get back are 2 different points. So, it is certainly not 1 point. So, it is hard to represent. Same thing you can see about polygons. Okay. So, in order to represent those kinds of results, OGIS added another notion called geometry collection, and within which you have basic data types such as point collection, polygon collection and so on. Okay. So, they provide this nice closure so that you can do multi-step query, but they also provide simplicity of modeling. Now if you wanted to model Hawaii or Japan, which are collections of islands, then it's much simpler to simply use polygon collection and work with that. Okay. So, this gives you the basic data types inside OGIS. Now, let us go and look at the operations. Okay. So, OGIS also provides a set of operations which can be grouped into 3 categories. The first one is in some sense universal operations, and they are very simple, and here are some of them. So, a spatial reference is talking about a coordinate system. So, if you have ever played with map data, then you may realize that all the measurements come with a reference frame. If you have worked with, let us say, Google Maps, you might see latitude and longitude, which is a spherical coordinate. But if you have worked with other GIS data sets, you will realize there are many other coordinate systems. In fact, latitude, longitude, they model Earth as a sphere, but regional agencies, they prefer a ellipsoidal model, which is more accurate for a small region. Unfortunately, there is no unique ellipsoid. So, around the world there are hundreds of them. So, depending on which state agency you got the data from, they may use a different ellipsoid. And then if you are even in a smaller area, some people may use planar projections. Okay. So, cut the story short, there are hundreds of these, and it is important for your data set to specify which coordinate system they are referring to. Okay. Then they have other basic things. The envelope is operation which takes a polygon, it returns a bounding rectangle and so on. Okay. The second group tests for topological relationships. So, again if you look at dictionary meaning of topology, it is a mathematical notion. There is a branch of mathematics called topology, and it deals with those spatial relationships which are independent of your map projection. Okay. Not all properties are like that. So, in fact, if you want to look at things like distance or area, these metric properties, they depend on your map projection. And in fact, in the popular map projection which we all see on paper called UTM, the areas are highly distorted. Things closer to pole look much bigger than their real area. Things closer to equator look smaller. So, if you were to compare areas of Greenland and India in common maps, you will probably come to the wrong conclusion in terms of the order. Okay. But there are other relationships which are independent of map projection, where you see a map on a sphere like a globe, or on the paper, these relationships do not change, and they are called topological relationships. An example of that is this touch or neighbor. So, suppose I am asking a question, which countries are neighbors of USA? Now, this answer will not depend on which map projection you look at. On globe, you will still see Canada, Mexico and maybe Russia as neighbors, and so would you on a piece of paper. Okay. So, topology, this is where Max Egenhofer's thesis actually came in handy, and what he did was to generalize another one-dimensional topological model called Allen's algebra in artificial intelligence. He generalized it to 2 dimension, and he looked at many possible topological relationships, and he boiled them down to roughly half a dozen to a dozen, and he basically came to the conclusion that in most applications those are sufficient, and they are also mathematically complete. So, here are the representative ones. Okay. We already saw touch, which allows you to look at neighbors, whether 2 polygons share boundary, but you have other things like disjoint. So, if you think about 2 polygons which do not share either boundary or interior, then there will be disjoint. Equal means they have exactly same boundary and interior and so on. Most of these are pretty intuitive. I would say the only one which is not intuitive is cross. So, cross is a topological relationship between a linear geometry and a polygon geometry. So you can ask a river and a country. So suppose rivers are modeled as center line and countries are modeled as polygons, then you can ask which countries are crossed by river Rhine or Nile and so on. Okay. The third family has to do with the metric or measurement, and this is where things we are very familiar with such as distance come in, distance, area, and it also has geometric operations like convex hull and so on. Okay. What we will do is to try a few of these operations with SQL to show you how they are used. Okay. So here is a quick quiz that you may want to test your understanding of these operations for the query we just saw in the last video. So if you wanted to check origin as an inside point for rectangle, you may want to check which OGIS operator is relevant. Okay. Okay. So again, going back to SQL and OGIS, here is some other things to know about the vendor implementation, that they are supported by many vendors. However, the syntax changes slightly. Okay, so conceptually you are likely to see same data types and operations, but the way they will appear will be slightly different. Okay. So in case you want to run some of the queries we are discussing on a particular platform, you may not be able to take the code from these slides and run it there. You will have to check vendor specific syntax and comply. Now we do provide you at least 2 short articles to show you the format from Oracle Spatial and PostGIS, and these are provided at the end of this lecture. So those encyclopedia articles you can quickly look at before you go use those brands. Okay. So be aware of that. The queries we are showing, we are providing you an intuitive simple syntax, but they may not run on a particular product that you are working with. Okay. So next question, what do we do with the OGIS data types and operators? Where do we use it in SQL? And we say we can use it in at least 2 different places. First is data definition language. So if you remember that create table we looked at very, very early, probably second video in this module. In create table, we listed table name, then we listed a set of columns with their names and data types. Now in the data type, you could use OGIS data type. So a table can contain a column, let's say shape, and that could use either point, polygon or line string. Okay. We can also use it in data manipulation. So if you remember your select statements, insert and so on, so there again many of these data types and operators can be used, and in these slides we will actually show you a number of examples of select statements which are using OGIS operations. Okay. All right. So let's start with very simple examples. What we'll do in this video is to show you the simplest things like area and distance, so that we get a feel for what this syntax looks like. And then we'll come back in next video show you more details, particularly spatial join using various topological operations such as touch, cross and so on. Okay. And we may even show you more complex operators like buffer. Okay. So for now let's at least get started and see some very simple things. Okay. So here is the simplest query. You can think of it as the hello world of spatial SQL. Okay. So we are looking at, in this case, country table, and for every country we want name and population. And remember, those were already there in the table. So we just have to get those columns. But in addition, we want area. And if you recall the country table, there is no area column. The closest thing in the country table was the shape, where we may have a polygon provided. And that polygon may have all the corner points and their locations, but certainly area was not there. Okay. So in order to produce the area, now we can think about the OGIS operations, and there is an operator called area which can be called. So here is a quick syntax. So only one table is needed, country table. We pick the name and population just directly as columns, and then to compute area you can call the area function or method on the shape column in country. Okay. And this will give you the names, population or area of the whole country. Okay. So essentially in uses, the main thing to note is the following: the methods or the operations that are provided inside OGIS, they can be used in many places in select. Okay. But particularly if they return a number, okay, if they return a number or a string or a geometry, then they can be used in the select clause in place of another column. So here you notice name and population are actual table columns, but area is a function which is applied on another column. Okay. So this is one way to use OGIS operations. Let us look at another example, and then we will wrap up this first set of first video on spatial SQL, and we will come back see details in the next one. So, here is another query, and in this case we are asking for gross domestic product GDP and a spatial property, that is distance of country's capital city from equator. Okay. Again, equator you probably know is a great circle on earth which is equidistant from both north pole and south pole, okay, assuming earth is a sphere. Okay. So, again if you think about how to answer this query, first question you ask is how many tables do we need, and you can probably see the country table is needed, and that probably has all the information. So, we do not need to worry about joining things, it is also not an aggregate query. So, in this particular table we have gross domestic product. So, we can get that directly, but it certainly does not have distance from the capital city. So, now this second part, in order to get that we need to ask two things. So, first, does this country table have the capital city? And again from previous video you will recall it does not. So, in order to get the capital city I need to bring in one other table which is the city table, and in the city table there is a column which says which country the city belongs to and whether the city is the capital of the country or not. Okay. So, just to get the capital we will need to join city table and country table, and we did that before 2 videos ago we saw that. Okay. So, I will assume that that part you are comfortable with. Okay. And then once we have done that, then we can look at the coordinates of this city and try to compute distance from equator. Okay. So, here is what we actually want, country name, GDP and distance from equator, and in order to do that 2 tables are needed as we just discussed, country and city. These tables are joined using a foreign key primary key join, there is no spatial join yet. So, you match in the city table there is a country column, you match it to country name, and once we have done that then for every country we will have all the cities there. You can add this constraint that this city is a capital. So, now for every country we have the capital, and then finally in the select clause we can put the GDP as well as this distance, and this distance takes the city's location xy coordinate, and here it creates a new point. So, this is a constructor where it says that the latitude is 0 and the longitude is same as the longitude of the city, right. So, this is a way to mock up equator, okay, and then you call the OGIS operation called distance in order to compute the distance. Okay. So, this is a little bit more complicated query. Here we did use 2 OGIS features. We used distance operator, we also used the constructor called point, and that together gave us the distance of a city to the equator. Okay. So, we will wrap up discussion of the first discussion of OGIS at this point. In the next video when we will come back we will show you spatial join and more details of OGIS. Okay. So, here is another quiz that you may want to look at in order to exercise your knowledge of OGIS operations.